In Python, calculating the exact time difference between two dates is crucial for mastering performance benchmarks. For instance, tracking a script's precise start and end timestamps allows us to measure its execution speed flawlessly. To do this, we rely on the incredibly powerful time delta object, which captures elapsed or remaining time perfectly. Let's look at an example. First, we will import from the datetime module, bringing in the highly useful datetime class. This class unlocks essential features, like fetching the exact current time right now. Now, let's set a deadline. We will use the end of the year, the 31st of December, 2026. Our goal is to compute exactly how much time is left. Let's check out our very first calculation. Deadline minus today. Once executed, look at the result. It prints out a clean duration, 198 days, followed by 7 hours, 14 minutes, and 48 seconds. It calculates all the way to midnight on December 31st. Since our current time is 1645, we can observe how dynamic this calculation is. If I scale the year up to 2036, notice how the total number of days jumps. The scale continues to grow seamlessly. Let's push it further to 2056. As you can see, the output consistently structures itself by days, hours, minutes, seconds, and microseconds. Days remain the core foundational unit. This is a vital distinction. Now, let's examine our second scenario, where we benchmark a program's start and end times. We'll run a quick loop to measure execution speed. And here's the precise duration. Notice that this output omits the days segment entirely, displaying only hours, minutes, seconds, and microseconds. Let's inspect the underlying data type by printing out the remaining variable's type. As expected, it belongs to the datetime module's time delta class. If we run the same check on our loop duration, it confirms it is also a time delta object. Remember, time delta inherently tracks everything: days, hours, minutes, seconds, and even microseconds. When a difference spans less than a single day, it cleanly hides the day count to keep output sleek. This smart formatting is incredibly useful to remember. It makes measuring execution gaps in Python an absolute breeze to implement. Keep in mind, time delta is the core class. It prioritizes days because they are a reliable, constant unit, making them perfectly predictable to calculate. Unlike months or years, which constantly shift, why does Python default to days? Because a day is always fixed. Months fluctuate between 30, 31, or even 29 days. And years vary due to leap years. Days avoid all that chaos by sticking to a standard fixed unit. It remains precise. That is the magic of time delta and its foundational format, giving you total control over internal application timing. Just use the standard minus operator to fetch your time delta and unlock a world of precision. Calculating time gaps in years, months, and days is a common challenge every Python dev faces. The standard datetime class is perfect for tracking now. I've got the current time and a future deadline. Let's say my retirement in the year 2065. I'll set that as my target date. Simply subtracting now from the deadline gives a total. Running this script outputs 14,443 days, a huge, unhelpful number. Dividing by days per year gives roughly 39 years. But this approach fails because of leap years. Some years have 365 or 66 days. Manual calculations quickly become inaccurate and messy. Trying to extract months is even harder. Getting exact years, months, and days is frustrating. It is far too cumbersome to handle manually. Luckily, Python has a powerful tool for this, the relative delta class. This is a game changer. It is fully aware of complex calendar logic. It lives in the date-util module under relative delta. Check out how clean this output becomes. It is incredibly simple. We get exactly 39 years, 6 months, and 15 days, remaining until December 31st, 2065. Forget the manual math. That was the old way. That was bad. That was wrong. This is the right way. Here's how it works. Instead of simple subtraction operators, we use the relative delta constructor, passing in both the start and end dates. It handles the rest perfectly. Amazing. It calculates the exact years, months, and days left over. Displaying that is a breeze. Think about how hard it would be to calculate each part. Individually, it is too much. Forget it. This even handles hours if you need them. Let's add that to the code. I'll update the script to include hours in the output. Running it one more time. Look, 39 years, 6 months, 15 days, and 6 hours. This is professional grade work. Use relative delta for clean time difference calculations. One detail to keep in mind, total days can only be obtained with the standard datetime class, not relative delta. If you need the total raw count, stick to the standard minus operator. Relative delta is for human-readable breakdowns. The days shown here are the remainder after years and months are set. It is a relative format, perfect for reporting the time accurately. In Python, you can't simply cast a time difference. For example, look at this datetime module where we import the datetime class. Right here is our standard class. Notice how we are calculating a deadline for 2065. On December 31st, we find the difference using the minus operator. Now, you could try a rough estimate using 365 days, but leap years have 366. The minus operator just gives you the raw remaining days. It returns a time delta of over 14,000 days, which is equivalent to roughly 39 years. But here's the catch. Once you get this total, you lose the timeline context. Why? Because it forgets the start and end dates. You are just left with a massive pile of days and hours. There is no way to reverse engineer the original dates. Was it 2065 or 2075? The timeline context is completely gone. Enter relative delta. It is fully calendar aware. It perfectly tracks exactly how many days are in each year. It accounts for leap years, knowing exactly when they hit, from 2026 all the way to 2065. It maps out everything flawlessly between those dates. That calendar data is built right into it. This makes it incredibly context-aware. Relative delta handles the nuance, while standard time delta is just a blunt, straight-to-the-point day counter. With relative delta, you can easily break it down into 39 years, 6 months, 15 days, and 6 hours. See how clean and readable that information is? To do that with a standard time delta, you'd have to divide manually by 365. But remember, years aren't always 365 days. Leap years have 366. Hence, casting fails. Let us check the object types directly. See this? We run type, printing the results to the console. It clearly shows datetime.timeDelta. Now, let's inspect the other class. Printing its explicit type signature, it originates from dateutil's relative delta. See, one is explicitly a relative delta class, while the other is a standard time delta. They are completely distinct types. Casting is impossible. You might get a time delta and think, I'll just convert it to a relative date, but Python rejects this because the object lacks any knowledge of the original starting points. When evaluating a simple subtraction, you only receive the final difference. You cannot reverse engineer the calculation, as those days could span any period. In contrast, relative delta compares two active dates, linking the deadline directly to the current date. It remains calendar aware. Lock this critical distinction into your mind, and never forget it. It is an absolute game changer when mastering Python dates. If you loved this tip, hit like, subscribe, and drop a comment. Help us grow and bring you more awesome content. Did you know Python has powerful built-in math tools ready to go? Let's explore these functions. You have max, min, absolute, and power functions. These work immediately without needing to import any modules. However, tools like square root, ceiling, floor, or pi, these are not included in the standard Python library. But max, min, absolute, and power certainly are. Consider these weekly sales figures. We want to find the highest and lowest sales for the team to quickly identify which team performed best or which team struggled with the lowest sales. Simply use max and min. They are built right into Python. No imports required at all. But if you need to calculate square roots, ceiling, or floor, you must import the math module. The math class holds those, while the basics we just saw don't need any external help. They are already part of Python. Notice here, we are working with a list. The max function accepts any iterable object. Keep in mind, any iterable, it will instantly find the maximum value. For instance, I can easily switch this to a tuple. I'm updating it to a tuple now. Observe the two round parentheses. By changing it to a tuple, it still works perfectly. The code remains solid. I could even use letters instead. Let's see. Here, I have a sequence of letters. The highest letter is E, and the lowest letter is A, so max and min are incredibly versatile across data types. But remember, for advanced math, use the math module. You must import it before using those features. If you forget to import it, you will trigger an error. It will say math is not defined. Even if you try calling it directly like this, Python won't recognize square root. It isn't a built-in command. Python won't understand your request. That is why you must use the import math command. Then, access the math module. This unlocks the square root, ceiling, floor, and pi tools. The Ceil function is an absolute essential in Python with incredible real-world uses. Let's dive into a clear example. Imagine building a smart inventory system for a massive warehouse. Each shipping box has a strict maximum capacity of 20 items. Today, we have 103 products to pack. Remember, a single box holds exactly 20. How do we calculate the exact number of boxes needed for all these items? To find out, we run a straightforward mathematical division. It's a simple formula. Divide the total products by the capacity per box. When we execute this, look at the result. We get 5.15 boxes. But here's the catch. A warehouse cannot provide a fraction of a box. We must round up to the next whole number, which is 6, to so. I highly recommend utilizing Python's built-in math module. Simply import it, and you gain access to the powerful Ceil function. As you can see on the screen, this function takes a numeric input and returns its upper ceiling value. Think of it just like a physical ceiling. Every room has a floor at the bottom and a ceiling at the top. The ceiling always represents the highest point. It pushes everything upward. That is exactly what Ceil does. When given a decimal value like 5.15, it automatically rounds up. It scales directly to the next nearest integer. Let's comment out the old line and activate our new Ceil function. Watch the magic happen as it outputs 6. Perfect. For 103 products at 20 items per box, we need exactly 6 boxes. To safely pack everything, super useful. Just remember to import the math module first. It isn't available in standard global scope, so that import statement is vital. Make sure it's at the top of your file. Next, simply pass your division calculation or any floating point decimal straight into the parentheses. Python processes it instantly, giving you a clean, perfectly rounded whole number every single time. I use this function constantly. It's a complete game changer, so start adding it to your code today. Let's explore JSON, which stands for JavaScript Object Notation. Many beginners get confused by Python dictionaries and the JSON format. Today, let's clear up those differences once and for all. First, you need to realize that a Python dictionary looks almost identical to JSON. You will see familiar curly braces, along with key and value pairs. When we run this code, we can see the output of our dictionary. Dictionaries rely on these specific key and value pairs. For example, the name is Sarah, and her age is 32. Sarah is also marked as an active user, but check the class type. When I print the type of this variable, it confirms it is a dictionary object. This means it comes with all the built-in dictionary functionality. If I type a dot here, for instance, you can see all the methods available to a dictionary. Everything a dictionary data type should possess. So that is our dictionary class. Now, to work with JSON, first you must import the JSON module. Yes, the JSON module. And here's our dictionary already defined. But look at what happens when we use that module. We access the JSON module, and within it we call a function called dumps. We pass it our Python object, in this case our dictionary. At that point, the resulting data from the dumps function is stored inside this JSON data variable. Now, when I print this, you might think, wait a minute, the dictionary output and the JSON output look identical. They are remarkably similar, aren't they? But if you check the type of our JSON data, notice it is a string class, whereas the other was a dictionary class. That is the vital difference. When you attempt to run actions on it, you will notice that we get entirely different options to work with. It is effectively just a string. All the functions available now are related to strings. Exactly. While with the first one, you saw that we actually had standard dictionary options available. That is the first major distinction between them. One is an object and the other is a string. This is a Python object, and although JSON looks similar, it is technically a JSON format, which is stored simply as a string in Python. The dumps function's only job is to serialize an object. In simpler terms, to convert a Python object into a JSON string. This is crucial. It is a JSON formatted string. That is why the output is a string type. It formats the data as a valid JSON string. And that is your introduction to JSON and the primary difference that often confuses beginners. I hope this clears it up. If it did, be sure to follow, like, and subscribe for more. Python can automatically map JSON data into native Python types. Let's see this in action with a practical example. First, we import the JSON module. This module contains essential tools for handling JSON data. It comes standard with Python, so it is available everywhere immediately. No need for pip installs, it is built right into the language. It is ready to go. Imagine you have received this response from an external API. This is the raw JSON string format we are working with. To process it, we use the JSON module and its loads function. The loads function takes a string literal as its input. When we pass this JSON string to it, it automatically converts it into a standard Python dictionary. Notice how the structure mirrors Python's key-value pairs. When we run this, the data is successfully converted. Let's print the result. It appears almost identical to our original input, but check the class type. It has been correctly identified as a dictionary, thanks to the loads function. Now, what if you receive a JSON string that looks like a list? When you run the code, the loads function automatically creates a Python list object. It intelligently identifies the type. It does this by checking the very first character of the string. If it sees a curly brace, it creates a dictionary. It maps it perfectly. If it sees square brackets, it knows to map it to a Python list. That is how the loads function intelligently handles conversions. Let's dive into working with JSON in Python. Handling JSON in Python is incredibly intuitive. Consider a standard Python dictionary. We know how these work. They use curly braces and store data in key-value pairs. For example, the key name has the value James. Then we have age mapped to 41. Notice how the keys and values are linked by a colon. The colon clearly separates each key from its value. Each key-value pair is distinct and well-defined. We use commas to separate these pairs in the list. Each key is unique. Also notice that entries like projects contain a list. This is important. You are nesting a different data type, and we know lists well. They start with square brackets, with items separated by commas. It is exactly what you would expect from any list. Think of it like a simple handwritten shopping list. It's just that simple, and dictionaries are just collections of these pairs. Now, here is the secret to converting this to JSON format. We use the dumps function from the JSON module. See how effortless the conversion process is. Just call the module name, then dumps, and pass the data. It instantly transforms your Python object into JSON. Let's see what happens. Watch this. Running this code results in a structure that looks like a map. You still see the curly braces, the colons, and the commas, but pay close attention to the specific values. Names and strings generally stay exactly as they are. Ages remain unchanged too. But look at premium. Here, the value is true. Note that Python uses a capital, while JSON prefers lowercase. Python uses a capital T because it treats it as a constant. However, JavaScript uses all lowercase for its own reasons. The designers felt that was the best approach for the web. Python remains consistent with its own capital T convention. These are constant types, the same as none. Everything converts automatically. The dumps function handles the heavy lifting, formatting it for JSON. It is perfectly seamless. It shifts right into the new format. Everything is converted. Even the none value in Python, which represents missing data, is automatically mapped to null in the JSON output. You do not need to do any extra work here. It just happens for you. The list data type is also converted into an array. Here are the simple rules. The dictionary becomes an object. This is the JSON object, starting with curly braces. It is no longer a dictionary. It is now a JSON object, and the list is now referred to as a JSON array. This follows standard JavaScript array syntax. Python strings and integers map directly to JSON types, and none becomes null, the standard for JSON. Unlike Python's none value, I hope this simplifies the JSON conversion process. A single function handles everything from true values to null and arrays, bridging Python and JSON. Remember, use dumps to turn Python objects into JSON. I hope this lesson provided clarity. If it helped, please like, subscribe, and leave a comment to say thanks. Let's master JSON formatting within Python. Today, we dive deep into making your JSON clean and beautiful. I'll break it down step by step so it's incredibly easy to follow. First up, let's look at our import statement. We import the JSON module. So simple, it comes standard with Python, meaning 0 extra pip installations are required. Everything is built right into the core language. Imported in, we set up a simple Python dictionary. As you know, dictionaries use these curly braces with key value pairs cleanly separated by a colon. Each distinct pair is separated by a comma. Take name, it's Emma. Engineering depth, and a salary of 65,000. Okay, next, we can effortlessly output this data structure by calling the dumps function directly from the JSON module. This instantly converts our Python object into a perfectly valid, standardized JSON string. You don't have to write any manual parsing code. Python handles all the heavy lifting for you. When you print this string or save it to a .json file, this is exactly what you get. All pairs appear on a single line. While it's valid JSON, it's definitely not pleasant to read. While it's completely valid JSON, it's tough for humans to read. To fix this, we can pass an extra parameter into the dumps function. Right after our dictionary object, we add a comma and set the indent parameter equal to 4. This instantly transforms that compressed string into an elegant, beautifully organized structure that anyone can read. It's essentially a pretty print. You might know this as a pretifier. Watch how it automatically formats fields, introducing structural upgrades from our previous version. It seamlessly injects new lines and assigns a clean 4-space indentation, 4 clean spaces. Looking closely at the output margin, we can trace each one individually. 1, 2, 3, and 4. Those are 4 precise space characters injected automatically. 0 tabs are used. When it comes to JSON syntax, remember this fundamental rule. Indentation does not alter the underlying data structure. JSON completely ignores whitespace outside of strings. In production environments, most APIs will use a 0 spacing layout because eliminating spaces reduces payload sizes, making this minified format optimal. But during local development, a pretty printed layout is incomparably easier to scan compared to a dense block of raw code, and it's a lifesaver for massive data files. Just remember, indentation changes absolutely nothing about how the machine processes JSON. Its sole purpose is to rescue human eyesight. That is its only job. It makes absolutely 0 difference to how Python parses it, or how any other backend JSON processor handles the data. Adding space is purely about aesthetic clarity, and these white spaces hold no semantic value, they just look good. We all know that in Python itself, indentation is strictly enforced, defining logic, but not in JSON. JSON completely ignores spaces, so choose the layout that fits your immediate workflow. Up to you. Keep in mind, production APIs will almost always serve the minified layout. To slice off unnecessary characters and maximize network speeds, expect to run into compact formats across live web servers while reserving pretty printing for local debugging sessions. If this leveled up your Python skills, hit subscribe and drop a comment.